Welcome everyone for the talk of Michalis Uniotis. Michalis has made his studies in astronomy in Athens, master and PhD from 2011 up to 2017. Then he moved to Czech Republic, where he's doing a postdoc since 2017 in the Astronomical Institute. His expertise is mainly in massive stars since beginning, early variables, binaries, and evolved hypergiants in the local group. He's visiting us for 2 months in the frame of the project Poems. So, welcome.
Many thanks for the invitation, also for the hospitality, the observatory. I have a pleasure to work with Lydia Stahl and the group. So, thank you for the introduction. And postdoc, I'm working on massive stars, in particular evolved massive stars, yellow hypergiants, which maybe very few of you may have heard. I consider it as a missing piece in the late massive star evolution, mainly because the observational evidence is very small, and the group of people globally that work with yellow hypergiants is quite small compared to the OB stars, the red supergiants, and then also other earlier types of massive stars. So. I think it stacks. Maybe it's better. Okay. Yes. So this is the so-called Russell diagram of stellar evolution. Massive stars begin their life in the main sequence. This part of the main sequence, they are stars with mass more than 8 solar masses. Due to the initial mass function, they are intrinsically rare compared to the low mass stars, and they live a short but very interesting life, impacting life, in the sense that they can change, they can alter the chemical composition in the surroundings. Also, they can regulate the physics of the ISM, mainly with the mass losses. At the steady mass losses in the beginning, the outbursts in advanced phases, and the supernova explosions at their death. So, massive stars, when captured at different evolutionary phases, they display several spectral types. So, we have the OB stars, which are the most long-living of the massive stars. They spend 95% of their life in the main sequence. So it's a long-term and steady impact with low mass loss rates compared to the advanced phases. And then the mass loss and the mass, the initial mass of the stars, tells us, and this seems to be in consistency with observations, what evolutionary channels the stars will follow, and the type of their death. So having that said, up to 20 solar masses, they evolve up to red supergiants, where they explode as type 2b supernova. Above 40 solar masses, they do never evolve as red supergiants because they are stopped by the Eddington luminosity. They cannot develop that low temperatures. That would be very destructive stars. They are blocked by a limit which is somewhere here. It's called the Humphreys-Davidson limit. And when the stars approach that limit, more than 40 solar mass stars, they exhibit strong instability and outbursts which shift them beyond the Humphreys-Davidson limit. These are the so-called luminous blue variable stars. A star that has suffered a lot of intense mass loss and has lost a significant part of its outer envelope can then evolve as a wall-fragile star, this part, but which has also spectroscopically different flavors. Other stars show carbon, other nitrogen, and also its function of metallicity, so the picture is more complicated. And it is also complicated the fact that Wolf-Rayet stars you may have from different evolutionary channels. For instance, you may have Wolf-Rayet stars from binary interaction. A star which can go as low as 9 solar mass can appear as a Wolf-Rayet star if it has been stripped by the companion. These are essentially helium cores. They are stripped stars where you cannot even define the radius. You work with the optical depth to characterize the star. Wolf-Rayet stars die as type 1 BC supernova, hydrogen deficient. They have lost in the process the hydrogen envelope. Meanwhile, up to 40 solar masses, you may have like and even more the B-bracket supergiant stars. This is a hybrid nature. This is, again, the channels that lead to B-bracket supergiant are not specific. You may have B-bracket supergiant post-main sequence or post-red supergiant as well. And the relationship with the systems and how the companion would trigger the appearance of the appearance of B-bracket supergiant is also should take into account. So yellow hypergiant here, I would say, are the least explored stars. Yellow hypergiants are there to justify the so-called the red supergiant problem. What is that? So observations in the local group, for example, the Levesque et al. 2006 in the Magellan clouds, have proceeded to a census of red supergiants here in this part, where they show with the updated models that red supergiant can reach up to 25 solar masses. But here comes the problem. The work from SMART 2009, very effective work, when they explored the pre-supernova images from Hubble Space Telescope of famous supernovae, they found that the upper mass limit for the progenitor is 20 solar mass. So it is natural to question what happens to these red supergiants up to 25 solar mass, how they die. So one explanation could be observational biases. These stars are enshrouded by a lot of dust and you miss them, or the luminosity, I mean, it's overrated, respectively. The other scenario is that also may collapse directly as black holes. This is more prevalent in low metallicity environment, such as the LMCs. But the most prevalent scenario, based on which also the recipes for the evolutionary models are built, are the mass losses. So stars, red supergiants with high masses, also exhibit high mass losses, which can literally alter their appearance. Here is a theoretical framework by Yu and CASLEO, who used hydrodynamic models of pulsationally enhanced, pulsationally driven enhancement, let's say, of mass loss in the red supergiant phase, and in the form of a super wind, and they calculated the mass loss as function of the evolutionary moment. Here are tracks of 20 and 25 solar mass as they evolve, and this point, and this is the corresponding mass loss for the 25 and 20. And at this point here, the dot here corresponds to the peak of the mass loss. So these authors, with some enhanced recipes, they found that the stars can even reach mass losses of 10 to the -3 solar mass per year in that very edge point. This means, of course, that in 1,000 years you lose 1 solar mass. And if you just integrate with this small but impacting tiny time scale, you can have even few solar mass that have been lost during the red supergiant phase for the most massive red supergiants. In fact, the recipes, the X-chrome, at least the recipes predict that a 25 solar mass star may even lose half of its initial mass during the red supergiant. And how is this translated? This translated as stars which lose a very large part of the hydrogen mantle envelope. So they expose their inner layers and they appear hotter. They start evolving hotwards. These are the so-called post-red supergiants. So they evolve toward. This is maybe the first census of yellow hypergiants by the year 1998, which yellow hypergiants here, to separate from the yellow supergiants, are exactly based on the status. Yellow hypergiants are believed to be post-red supergiants. And there are very few, and don't think that the picture has changed significantly since 1998. There are still very few stars known. These are constrained here in this part, above the luminous spot. And the most interesting fact for this are the outbursts for which I will talk in a while. These are constrained poolwards of an instability strip zone, which theoretically earlier has been already known to show negative gravity accelerations. The algebraic sum of different acceleration components, pulsations, you have turbulence, gravity, of course, the wind, gets to close to zero values, even negative. How this translates? Stars in this area are shown to have very extended atmospheres. They develop also negative density gradients, and they display high atmospheric instability. So what is known is that when stars approach a certain temperature limit, which is still not very secure because of the statistics, it's believed also that there are two actually strips there. A certain temperature which is associated with the partial ionization of hydrogen, the release of the recombination energy, can drive outbursts, flow of material outward. This is a census that I made quite recently. The current status, these are the yellow hypergiants here, and for comparison, I show also the big bracket supergiants, part of which are also believed to be bracket supergiants, to be post-red supergiants, or even post-main sequence. So we have a large population, but it is unknown whether they come from. However, it has been proposed by the similarities in the appearance, for instance, this, that this may be the descendants of yellow hypergiant, but maybe they are not. The picture is quite complicated. But still, the classification of these two different classes are different. So this mainly show characteristics of a disk. This is a strong characteristic of the supergiant, and hot dust, and the spectrum you see emission of iron, while these are mostly prevalent during the outburst. Otherwise, they have a typical yellow high luminosity star spectrum with very broad lines due to macro turbulence, the large scale motion, and they exhibit outbursts. So when they approach about this limit, like here, they display optically thick winds, which actually they are called pseudo-photospheres, outbursts, which drive dense swept-up material, and this dense material mimics the effect of a photosphere, and they start appearing cooler. And when the gas dissipates, they return to the previous pre-explosion state. The most iconic yellow hypergiant of these four that in outbursts, about 10 in total, 4 in outbursts, it's a star Rocas, which is one of the brightest stars in the galaxy. And for this reason, exactly, it has allowed accessibility with high resolution instruments and very thorough monitoring. I would say that the most spectacular recorded outburst of rock ash was the Millennium outburst in 2000. You see here the timeline of the star from the American Variable Society monitoring in the Big Bang. And at some point, at 2000, the star displayed the brightening here, and suddenly they dropped the magnitude by about 1.5 magnitude, which has been modeled by Lobel et al. 2003 using high resolution spectroscopy, not a WHG to this process, as a drop in the temperature of the star, about 3000 Kelvin. This is a very spectacular outburst which lasted about 200 days. The star recovered back to its previous state. Here, the spectrum shows the appearance of TiO lines, titanium oxide lines, typical for cool stars. While in this brightening point here, it has been suggested to be the collapse of the atmosphere, the compression of the gas, this converting to ionization energy, and the release of the recombination energy drive adiabatically expansion of the atmosphere very steeply. See, fast. This cell has been modeled to be contain a mass of the order 10 to -2 solar mass. The outburst was repeated in 2013, recorded by Kraus et al. 2019. They had spectroscopy from Perek telescope in Czech Republic from 2010 to 15 are the observations. This had a similar drop in the temperature, about 3000 Kelvin. The magnitude is about half, so it is not as, let's say, dramatic as shown as in 2000. But this work also provides study of different, the kinematics of different lines arising at different depths and traced alongside the pulsation. So STAR also showed asymmetric lines that are superimposed by circumstellar emission, the origin of which is suggested to be back from the red supergiant phase, a remnant from the red supergiant phase. And recently, more recently, I would say, Maravellas and Kraus presented the light curve from the 40s of the star, from AHO, where it is recovered the strongest, maybe, outburst of the star in 1946. However, unfortunately, there are no studies with those spectra of the star, so we don't know much about this. But I think that these are from the AHO, these observations are more like rely on the visual perception of individuals. So you have a large uncertainty. The data, of course, are beamed to account for this effect. But here the evidence is that here you have a very dramatic drop. And the frequency of the events, as well as the duration, changes, becomes smaller, and this has been suggested to be evidence that the star evolves outward and is ready to cross the yellow void and appear, as I said before, as a B-bracket supergiant or as a well-defined star. Another one was IRC 10420, a very also bright yellow hypergiant. It is inside the yellow void. The star in 1994, with the WHG data, was found to have an A2 spectral type, but back in the 1973, it was reported to have an F8 type, like that one. Although I have to be honest, I have to repeat, I said to Lydia, story. When I went back to the paper, this is from Humphreys, 1975, they report that the star had this spectral type, like an F8, but they don't show the spectrum. They just say that this was underexposed. So we just rely on this statement. But of course, one cannot can tell the difference between an F8, which is metal line rich, and an A2. So the star did appear, did change its type within 20 years. The star also saw a blue shift ejecta, is viewed all on with the jet that is pushing material towards the observer side, and has a high extinction, also developed high extinction. The EB minus reaches 2.7. That has been measured with the DIBS lines, diffuse interstellar band. Another one is HR 807052, for which they had high resolution spectroscopy from 73 and beyond, before that point, relying just on pure photometric observations, where the authors, I cannot even tell this in full extent, they reported that the star suffered multiple ejections of mass, and at this point, the star eventually clears out, so it reveals what the previous states. Now, beyond the galaxy, the only well-established yellow hypergiant is just one, and this is VAR A. This is captured in M33. This is one of the brightest stars in M33, actually. So the interesting fact for this star is that the star changed its spectral type from F to M, and this change stayed for almost 50 years. This is the most long-term maintenance of this status of a yellow hypergiant. In the 50s, you see here the brightness of the PV, and the color was of a blue star, which dropped suddenly, and it started recovering only in the end of 80s. The star saw also calcium triplet, forbidden calcium, H alpha emission as well. Things that these stars are not as accessible as Rocas. Of course, this has a 15 magnitude, so it's very limited, the studies on extragalactic beyond at least the Magellan clouds. Here is the SD of the star, and corresponding to the 50s, a hot star, 86, the dust obscured with evidence of excess. The stars in 2004, the dust has started clearing out, but still the star remains obscured. Possibly the flux is escaping away from the line of sight. And this is VAR A, the spectacular VAR A. So in this spirit, we also, in 2017, as part of my thesis, proceed to discover more yellow hypergiants in M33. We studied the most luminous yellow supergiants, because you expect that you find yellow hypergiants with the yellow supergiant population. We studied the light curves of these stars as part of a project which originally targeted Cepheids, but had monitoring many stars. Built the SDs and also got spectroscopy with GTC of the dustiest stars. And during the process, we reported a star which shows emission of cool and hot dust. It was found that it had calcium triplet in emission as evidence of an extended atmosphere, just like you saw before for VAR A, and the broad H alpha with side components. This is a very good evidence for yellow hypergiant, but most importantly, the light of the star is here, which when we complement it with the different survey data alongside the original the original set of data we work with, this revealed a possible dimming event that took place around 2000. Unfortunately, we don't have here observations, but when we model the temperature, we found that pre and post this speculated event, we have a change in the temperature. So what happened here is will be stay unknown, but we know that the star cooled in this phase, just what we expect from yellow hypergiant, and it's gradually recovered. So we suggest that this is another yellow hypergiant. This is that one. So stars, yellow hypergiants, are known also to surround by nebulosity and cells, as detailed studies in the galaxy, of course, are showing, but this is not always the case. For example, rock gas does not show evidence of nebulosity, only a bit after the outburst, but nothing more. So it is just like nebulosity, it is not really a strong diagnostic actually for the star, because a strong feedback from the star can dissipate the gas as well. So stars in the yellow hypergiant of the galaxy show some very interesting appearance in the frame of nebulosity shells. For example, Hypergiants et al. 2013 discovered a dusty cell around the yellow hypergiant Ken 1379. This is with capital imaging at 70 and 100 microns. This is a composite image, which they nowadays is known as the fried egg nebula, because it resembles the shape of a fried egg. This has been modeled, has been suggested, because this study is quite preliminary. It's followed by thorough studies by a gaseous shell of 7 solar mass. So this contains seven solar mass gas. The most thorough study, I would say, on the fried egg nebula was in 2020 by Kubja et al., who did proceed to interferometry of the star with the gravity, yes, where they got mapping at millisecond scales. They also complemented with imaging from VLT at infrared, where they assessed density profiles, and they used also 2-dimensional radiative transfer code to model the SD of the star in consistency with the density profile, and they proceed to publish the results being 3 cells, both intermediate and outer cell, containing the most outer of which 6 solar mass in consistency what said before, with different temperature from 600 Kelvin to 200 Kelvin. IRC 10420 is another yellow hypergiant which shows nebulosity. It is viewed pole on, and you just look straight in the equatorial plane. Starting from the cluster ratio was the radio telescope, the IRAM, the 30-meter single dish IRAM, where they did mapping of the CO channels. They show a spherical halo with evidence of some symmetries. They also modeled with a quite much more simplified than this approach the surrounding gas, and they found also evidence of 2 shells with mass loss of 10⁻⁴. The most distant shell is believed to be the result of an outburst that took place 6,000 years ago, and the most recent one about half of this time interval, with a mass loss ending about 200 years ago. With the Hubble Space Telescope, Tiffany et al. 2010 did a more detailed imaging star, where it revealed a more complicated structure with nodes and arcs and jets here within the expanding nebula. The nebula expands with a velocity of 30 kilometers per second, but these structures here show to be decoupled from these kinematics. They are suggested to emerge from different places, different areas in the photosphere of the star. So the expansion basis is 100 years. But the overall event that gives rise to the nebulosity is also about 6,000 years ago. What else about the star is that, as I said before, is in a yellow void, optically thick wind, and it is believed to that is about to shed its dense wind and move to the hotter dimensions. The circumstellar environment of a star is not a static state, but it is a dynamic state. So this is proved by the work of Gorlova et al. 2006, where they have the timeline of ROCAS that you saw before, the outburst of AHO, and they got spectroscopy low and medium in the K band of the star, where they modeled the CO bandheads, and they found that at different phases of the stellar activity, the profile switched from emission to absorption. This is the result of a pulsational driven shock waves, which span the atmosphere and modulate the properties of the systems as they compress the gas, so that the gas can attain densities suitable for giving rise to emission. They can seal the gas, so it is well coupled to the dynamics of the star. At phase of high mass losses, the star shows emission of CO. And the previous scenario that the lines, the split lines, are actually two components. It was now interpreted as being one static circumstellar emission. This is the CO line, which is here, it's the emission. And this is superimposed over a pulsating core, absorption core, which creates the illusion of two lines. So the authors speculate that it's just one static circumstellar line, which becomes stronger, excess above the continuum level at phases of strong mass losses. Of course, when we talk about the extragalactic space, you cannot have detailed interferometric studies, so you need to rely on more simplified but still very important tools. One such is the observations in the K band of the CO bandheads, as I said before. So typically, as also in B-bracket supergiants, we see emission lines in the CO bandheads, which have this profile and increase in the decade. This has been modeled. The big gas which accumulates in equatorial flow and is shielded in disc or ring-like structures, such to protect the molecule from the destructive radiation field. So these stars are actually hot enough to destroy CO. However, when CO is distributed over such geometries, it can be shielded and can attain high enough density to give rise to emission. So these are two yellow hypergiants in the LMC, and this is modeling with the radiative transfer code by Krauss 2000 with a disk or ring model. In addition, the stars show evidence of CO13, which is a material which is the result of processes in the core of red supergiants, and it is dredged up from the core to the surface, and it's been expelled. So the ratio of CO12 to CO13, here is the CO13, this line here, It's also a good diagnostic for the evolutionary status of the star. A low ratio means that a star possibly has been to the red supergiant phase. It's a post-red supergiant. So this medium resolution with PLT. 10 years later, with the help of our colleagues from La Plata, this star was observed with from Gemini North, from Gemini South, from North we cannot see, with a resolution of 45,000, much better resolution, where it has been reported last year by Krauss that the star showed evidence of water vapor, blue words of the CO bandheads, which is unbroadened and with cool temperature, so it is distance from the star, and this is the first evidence of water vapor around such type of stars. It has been shown for low mass counterparts. Also, we have a recent submitted work of CO moderate resolution spectroscopy of yellow hypergiants, where they show the profile, two of which shows an interesting data set. FMR 2006 show evidence of emission, which, however, was observed in 2005, showing weak absorption. And because the star is too hot to allow for the molecule to emerge, this is again the case of circumstellar material which is shielded. So it does show a nice variable circumstellar nature. Accordingly, a star which shows absorption here was found in 1989 with emission, like that. So it seems that this material has dispersed in the meanwhile, and what you see here, because again the star is too hot to allow for these lines to exist. We talk about material that has been expelled, but it's still close to the vicinity of the star, so you only see the interpolating absorption. You don't see yet the emission, but it's expected that continuous particle in the star will switch the absorption into emission. It is anticipated in that sense. Also, the star show over Abalo showed you another good diagnostic of a pre-red supergiant, or that the red supergiant phase has been already taken place. And in the optical, we have nice, also interesting line dynamics of the star. For ROCAS, you see that we talk a lot for ROCAS because it's the most well-studied star of the very few. In the 60s, it was first reported that the star shows broad asymmetric lines, with asymmetry being more evident for low excitation lines that emerge in the upper atmosphere. And back then, it was speculated that these components are of circumstellar origin. The spectrum of ROCAS, the detailed monitoring campaign of different high-resolution spectra, and here is the epoch of the outburst. So interesting H-alpha profile, where the most interesting characteristic is that prior to the outburst here, you saw a strong blue strip in H-alpha, which is the evidence of the collapse of the upper H-alpha atmosphere. And during the outburst, you see that the H-alpha core fills with emission, with shocked gas, shocked and recombining gas, and also show evidence of a redshift component as a result of the ejecta. The star also had a similar profile later, but did not proceed into an outburst. But this, I would say, is the most interesting feature. And photospheric lines also show the effect of pulsations, while lower excitation lines also show the split lines, like here, but now it has been interpreted to be a static emission intruding line, the pulsating line actually. So in 2022, we also did some similar work with, of course, fewer observations and not as detailed as the galactic, this is an LMC yellow hypergiants, where we present the dynamics of 4 different lines here. The green and the black are photospheric lines. You have the red, which is the H alpha, and the blue, the low excitation line of barium, also shown to be asymmetric for yellow hypergiant and grows in the upper atmosphere. And we also present nice results. These are data from Ferros, a shell spectroscopy. So, for instance, we reported a star which showed in 26 evidence of infalling shock gas here, and less than a year later, the profile changed completely into redshifted emission. So it's like an event took place in the meanwhile, and at the same time, the barium line was enhanced. So it seems that an event which pushed material out, and this material also replenished the circumstellar reservoir and give rise to a symmetric and strong barium line as well. Interesting results also for another level that was very extended, but I would say that 2699, the one with the water vapor, was first report here to show binarity. How? The iron line was found to be the double-peaked emission, and the BR ratio, as many of you know from the disk observation of disk of B stars, show modulation, and it seems that the system, this pattern orbits around the radial velocity of the star. We believe that it's a star, a yellow hypergiant, which is surrounded by a companion, which hosts a disk. And we also see that the barium line, which is a circumstellar origin, as I said before, the climatics are anti-correlated with also, so it's not like there is a coupling of the circumstellar with the orbital dynamics. This is a star for which I follow up. CASLEO will be very, very important. We have already other stars, high-level spectra, and if we manage to build the radial velocity curve, we'll be able to constrain dynamically the mass of the yellow hypergiant. And having that said, this would be a shame not to talk about binarity in yellow hypergiant, which is something only reported in one case, HR 5171. And this gives rise to the discussion why we don't have binaries. Are there observational biases? Do they end up as binaries when born as binaries, really? This is something which is under discussion. This is the case of 5171, a yellow hypergiant which is very extended. It has a radius of 1,300 solar radii. It is really in the edge. And it was discovered by CASLEO to be actually a binary star. So the authors used interferometric study with Aether, and they analyzed the flux, the images of the star, where they show that the best fit was found from the reconstructed images to have 3 components. A uniform photospheric disk, which is a star. We have a halo, which is a circumstellar environment. And we have an evidence of asymmetry in the flux, which is actually this dotted here, which is the hidden companion. So having 10% of the total flux. Indeed, star with Ipacos and ACE data showed evidence of eclipsing configuration. So this is a phased light curve of the star, shows nice eclipsing binary with an orbital period of 3.5 years. And this is the observations, the K band as a byproduct from ABER, as it also gives a byproduct spectrum. These are the observations of the star, and this is being decomposed into three components based on this geometric model. So we have the photosphere of the star, showing CO in absorption. We have the circumstellar envelope here, which is actually the black one, showing CO in emission plus an overabundance of sodium here. And as I said before, 10% of the flux corresponds to the hidden companion this year. And altogether give us the observation of the sun. It's a nice artistic impression of the study, a peanut-shaped star, where the companion is at about the distance from sun to Saturn. And here the nebulosity extends into 6,000 AUs. So what is this is believed to be in a width. Rosslob overflow does not really fill yet the Ross overflow, but the star is believed to lose mass, the system, hence forming the circumstellar nebulosity. And the fate of the star is discussed, whether it will be a Wolf-Rayet star if the orbit will shrink, or will end up as a long period binary if mass is lost from the system and angular momentum lost from the system and the orbit widens. And for the last slide, it will be not fair not to speak about pulsations. This is not much things are known, some speculations, but it is nothing solid. It's not well studied as in the OB cases. Stars on the majority yellow hypergiant show evidence of a pulsating behavior with an amplitude between 0.2 to 0.4, corresponding to temperature variations of around 500 Kelvin. These are light curves from known yellow hypergiants. This has been described by Van Gederen as chaotic nature. You cannot predict really the properties. You see uneven peaks and dims. You have evidence of multi-periodicity. These are believed to be non-radial pulsations from the study of frocas. Otherwise, a radial would create a conflict with the estimate of the radius. So they believe that there are non-radial pulsations, actually, mixture of pressure and gravity mode. But this is something which I cannot speak for sure, because my expertise is not that pulsation, but still, I can tell you that not much things are known. But we only see that the star is pulsating in a multi-periodic pattern. But it is well known that pulsations, when the star is close to the yellow void, can be facilitating the eruptions. They can push the star to meet the requirements for the ionization with the compression due to the compression of the gas. And yes, so pulsations don't much know. And of course, the pulsation may also modulate the circumstellar environment with the pulsation-driven shock waves, which propagate in the atmosphere and can compress the gas, such to get enough density and emerge the flux in the experiment. The most recent work from Dor Barenstein, 2022, they worked on a LMC sample of yellow supergiants, where they reported that the very luminous of the yellow supergiants, above 5, they displayed evidence of high frequency pulsations compared to the low luminous counterparts. And this has been thought to be the result of a posterior supergiant evolution. So a scenario is that posterior supergiants may be fast pulsators. However, I would say that I take with a grain of salt this study because it relies on a sample where temperatures are rely on a single color estimate and also to a global extinction value of each. So the HF diagram may change significantly. These are observations with TESS. So we talk about high-cadence, and modulation with a very low amplitude. We talk about amplitude of pulsation of 1,000th of the baseline level, which of course you cannot see in these studies. But still, it is constrained in a sample which is poorly defined. However, this study was actually the motivation for me to use the test data for the overall posterior supergiant sum, yellow hydrogen, B bright supergiant sum stars, and see if there is like features which we do not see in the pre-supergiant evolution and give an explanation. So I worked the last months on test data of posterior supergiants. I built some tools to analyze the stars. And when I came to La Plata, and this is the end of the yellow hypergiant talk, when I came to La Plata, I used these techniques over a different sample, over a sample where Lydia Stahl and her group works with B-supergiants, trying to understand the properties, the multi-pulsational properties of B-supergiants with TESS. I changed color consistent with the color of the stars, switching from yellow to blue. So TESS provided us from 2018 a high-cadence, high-resolution photometric data of stars distributed in sectors of 96 degrees times 26. So with respect to the position of the star on the sky, a star can be observed many times in many sectors. So the goal in this project is, as I said, given a sample of B stars for which there are spectroscopy from CASLEO, to first see the multiperiodic properties of the stars and then to associate with spectral diagnostics from CASLEO. But at this part, I concentrate on TESS. So I will just briefly show some snapshots from this process. So the stars, typically TESS provides stars a 2-minute cadence and 30-minute cadence data. The 2-minute cadence are for a targeted group of stars for which also their data are reduced, are cleared from the systematics, and also they have mask and aperture mask in the images where you can extract the data. Here I proceed to a more common practice to extract the images from the full frame images and provide my own mask and do my own clearing of the data. This is part of this process. So you see here a 2020 pixel of one of the big targets, where you see here it's the selection of the background with white and the mask with red. So in the middle panel, you see the lower part, the flux from the background, which reflects the effect of the systematics. This is the effect of scattered light, which is repeated within the time window of 29 days, 27 days, because the TESS within this window, TESS orbits Earth twice in this window. With red in the middle, you see the exact light year. So what I did here, I correct the background with the principal component analysis. I analyzed the background into different principal components, and then the regression of the data was based on these components. Because these targets are very bright, realize that even one component is enough. So here you see the clearance of the data with one component, with the two, and then with the three components totally mess. Because these are very bright, and with one component, just removing this strength is sufficient, and that's it. For 10 targets that I work with, in Czech Republic with post-supergiants, which are 14, 15, the need was to increase even to 3, 4 components, but here it's not the case. Mainly because the third component here actually has activity from the star, somehow it's contaminated here, and obviously you don't want to remove the activity of the star from the star, and this will result in a noise spectrum. So with one component you have this nice light here. This is another process images. So you have here the selection of the mask. It's based on a threshold that I set with respect to the central pixel that hosts the star. Here I superimpose data from Gaia. The central pixel starts from where the Gaia is. Exactly the same process with one component physical analysis. And here is the extracted and corrected light. This is a very known, a very clear binary, eclipsing binary. Then I follow normalization process. So the data, the normalized data are here. Also something similar for another of the B-supergiant targets. And then I extract the frequencies to get this, the footprint of the star, the periodic footprint star. So I did log scar periodograms where I pre-widened the data. So each time I removed the highest peak frequency and repeat the process in the residuals until we no longer see peaks of significance. The termination criterion is still something which I work with. I have not decided on it, but when I reach the level of the noise, I stop. But this is something which I work with. And this is part of this process. You see, for instance, here the periodogram, here the log star periodogram. This is the light of the star. The red is the model at this frequency, at the highest frequency. And these are the residuals. The residuals give them a new periodogram, a new peak detected, and the model now incorporates two frequencies, and gradually the model, the multi-sinusoidal model, gradually fits the data. Here we have residuals which are very small RNS until we define one defines the termination criteria. And with this process, I extract the frequencies, the fundamental frequencies, combination of frequencies, for example, frequency 0 plus 1, have harmonics, and also have repetition of frequencies, possibly because when you use a sinusoidal curve and you fit a non-perfectly sinusoidal, you expect that you need more models proximate to this period to fit better. And this gives rise to unresolved, let's say, frequencies that have been already reported. So I do not count this. I just plug them. I count everything, but I just plug them. So having done this process, I end up into these preliminary results. As you see here, the fundamental frequencies with dense color. The data are binned as function of the speckle type of early B, mid B, and late B types. The types are taken from SIMPAD. So we take the grain of salt types which are 40 years old. That's why here the collaboration would be beneficial because provide temperatures with CASLEO, so we have accurate temperatures. But here I only show the symbol spectral types, where you see that the early types span frequencies, high frequencies, and gradually this becomes more solid, more dense in the short frequencies. When you zoom the distribution of the frequencies, you see that actually for early B stars, actually there is a tail of frequencies. Here this is a binary, and we just said that these are binaries, and accordingly it gives rise to the binary, to the tail in the harmonics due to that effect. And as you go to later types, you see that the distribution of the fundamental frequency becomes more solid, it becomes more compact. You cannot really define the central frequency of the fundamental part because you have this constraint from TESS, you cannot get periods more than 15 days. However, a nice tool which we're thinking now is to model the distribution of the harmonics, which essentially mirror the fundamental frequencies. And we found that they are pretty much the center of the harmonics is similar. There is some shift in the late types, but this is very preliminary because the numbers are very small. We need to increase our sampling. And this gives rise to the question that we had before, what happens to binarity? If this is our binaries here, the fact that the distribution becomes more solid has two explanations. Either you lose binaries in the process because they merge, or there is an observational bias which prevents you from seeing binaries beyond the point that you lose actually this state. Or the periods of the binaries shift into higher periods, and they are incorporated into a more solid distribution also. And the last slide of this talk, I was playing in this weekend with a simulator, which is provided by Nebraska, just so that take it with a grain of salt, how accurate that might be. There's a Eclipse binary simulator in the web, which we can use, can play, but of course is I'm cautious about this. So I generated a binary with consistent masses that of the sample we will work with. So we have a mass 14 solar mass star, 20 radius, and mid P spectral type 26,000 Kelvin. A hotter star, a more compact star, and a less massive star which has not yet evolved. These have a difference in the luminosity of 1 dex. And here I show the effect of the inclination of the system at 30, at 40, 50, and 60 degrees. How you can set the inclination plays a big role, of course, the appearance of the eclipses. So we can use to 80% of the central flux. Assuming that these binaries are detectable in the main sequence, that's why you have a high prevalence, and that the inclination does not change during the evolution. In fact, the opposite would one expect to happen. As the one star grows its radius, this encourages the eclipsing behavior. However, what can balance this effect, the enlarging of the radius, is a widening of the orbit. So the exact same system which gives rise to a detectable binary, 60 degrees, and even more, distribution is favors larger values. When you switch the exact same system in the separation from 30 solar radii to 50, you see that how you lose the effect of the pitches. So you go to almost undetectable levels, less than 1%. Just the widening of the orbit. Of course, the widening of the orbit means the enlargement of the period. So this has a period of 4 days, and this has 8 days. So remember, the shift here, the shift of the distribution from the change in this area, which is assumed to be binaries, would be actually the widening of the orbit, which results to a longer periods, more compact distribution. But only for frequencies that have been detected. Otherwise, you expect to have the hidden binary in the residuals. That's what we want to study. Whether the residual hide actually eclipsing binary activity, which is not anymore detected by the average surveys, unless you have, of course, the power of TESS. Here it's a case of a B8, a late type star. Of course, the light here is from the central star, and in the residuals, which are not in the statistics we showed before, the residuals, you see evidence of dims less than 1,000 flux, which may be actually this effect, the widening of the orbit. But still consider that this is blended also with stellar activity. So, but this again, it is very early to say, because the key for this conclusion should be statistics. So the next step is to increase our sample with a catalog of already of temperatures of P stars, hoping that something will be inferred. Whether this is an effect of widening of the orbit and the binary is still there, but need to be detected with the residuals. That's the case. And I did not use Barirato on this late type because we have to debate whether they are merging or they are there. So if it is there, it is also a late type, so it is there, but it is undetectable because the orbit widens. And why the orbit widens? Because of the non-conservative mass loss from the system. So the system will lose angular momentum, and this will mitigate stars into undetectable levels. This remains to be seen. And that's it.
Thank you very much. Thanks for this.
Thank you.
And I would like to ask you about the image to show from the budget of TESS. It seems quite extended. I'm sure it's strong.
Okay, so contamination, I do not talk about this because there are not much time for this. The contamination effect, so we explore the images in parallel with the distribution from Gaia source, and you have like a very strong source, which is from our source. The contamination will be approached differently. So what I aim to do, I already started, but in the process, I just put on the side. The frequency that we are from the central star will be checked for the flux of different pixels individually. So we think that if frequencies are detected only partially, for instance, if we have frequency peaks in the periodograms which are not globally seen but only partially, this will be an effect of contamination. So we put there a barrier. We will say that we accept frequencies above a limit. However, I do not expect that this would change the distribution of the fundamental frequencies, because the fundamental frequencies are the strongest, and this cannot be the result of contamination. So most likely a contaminant, like for instance, I don't know, like here, for instance, really will not have an effect on the distribution of the fundamental, the peak frequencies of the periodogram.
And did you try to run this TESS localized package?
The what? The
TESS localized package.
yeah, but it is yes, I know the recent paper.
Yes,
Yes, I haven't yet.
because for that package, if you insert the reference, you can derive the source of
You can derive. I remember where the source is.
where, yes.
Yes, so I went the opposite way. So I said where the Gaia source is of the target, and I assume that the pixel is the central corresponding to that. So I assume that I know where the. So here, for instance, this is the Gaia source, and this I assume that is the central pixel of the mask, where it starts from in the mask. And so localized provides also the distribution for the.
Because I was wondering, you might get some Gaia sources in that map where you put the mask. So I assuming that for that image, I don't see it as a single object in that image. That's why
So this is not, no, this is a single. This is a single. It's purely single. Yes, yes, and the flux saturates and spreads into the neighbor pixels. That's the case. If you see very bright 5 magnitude, you see that there is a huge column filling all of the field. So how the flux is distributed vertically, and then goes to neighbor columns. So this is just a single. So the other here, for instance, is very evident that you don't see Gaia sources. Here it's a Gaia source, but you see that even this one, which seems to be considerable, like this is the size is magnitude based. So the greater size is brighter targets in Gaia. You see that here does not even have test flux. You see?
Yeah.
So it's really they are really veiled by the star. Our stars are very bright. So the contamination, I don't think that is an issue for such bright stars. There is a case where there's contamination, like prevalent, but I think I can isolate the frequencies. But these frequencies will not play a role. They are not fundamental frequencies.
And you mentioned that the temperature will determine.
The what?
The temperature is will determine for the source. Okay.
The CASLEO. There are data for CASLEO.
Yes.
Not all are reduced, but they are in the process.
No, it's possible.
Ah, you mean the models are used? Yes.
Well, but if we can have 13 objects on my
Do you use special routines for using this data and or you?
So I have the package live here with K. It's written with K,
Yeah.
which has nice built-in routines for many of these processes. But of course, I pass them into scripting, Python scripting. So it's not just run. You need to do some scripting and adjust the routines.
These stars are not reduced at the test database.
I haven't checked which have a 2-minute cadence, and this may be useful to fine-tune the periodograms and compare them. But I know that not all have 2-minute cadence, so you have to do this process to cut from the images, from the full frame images. But some definitely, some of the very bright ones, for sure, they have 2-minute cadence. And they have the mask, but even the mask that the Spock provide, I have seen it's not really very reliable. Because, for instance, the Dorn Wallenstein, for the LMC, they use the Spock lighters. But when I applied the same data set, I saw that the effect of contamination is very evident there. Because it's the LMC, we talk about 10 magnitude, not 6 magnitude. And there, in LMC, you have there to account for the contamination. There it's strong. But in the galaxy, it's not that strong. It's not. So in LMC, you need to play with the mask. You cannot trust the mask. Many of these LMC stars are embedded within young clusters. They are contaminated by the pulsating behavior of OB neighbor stars. So you cannot trust.
Olivia, we can add also a seminar test reaction. Not only eyes.
Not only the eyes. So you have to be full seminars.
But you said, you said that answering to Julieta, that you search for frequency not as a code. You can distinguish frequency.
So in the beginning, I proceeded differently. I went to each individual pixels, I extract the flux, I extract the frequencies, and then I extract the frequencies of the whole. And I saw, and I checked which frequencies appear, let's say, in the 80% of the pixels. So this would be of the same star, the same global star. But if you have like frequencies which are only detected locally, these are not reliable. May not come from the star. Why should it come from here and not from here? Or it's from the star. Understand? But otherwise, in the peak frequencies are detected in almost all pixels. So from here to here, the same pattern.
And you search for this frequency
individually. Yes. But now I will go the opposite way, I think. So with a pattern that I have this frequency list, I will go back to each pixel and flag which are, yes, if I see, for instance, that some frequencies are only 10%, I will discard them. But again, this will not be the fundamental, the strong ones. Yes, so accordingly, it will not change our conclusion on this distribution, but on here, I don't think that. I will just remove some frequencies from.
how are the how many are the stars?
40, 45. I also have 5 stars which I need to analyze. I was like lately. But we want to extend this study to a catalog of B stars, like 100 stars from Fraser, for which temperatures are known to increase the statistics. But for this, you don't have CASLEO data, but in any case, this CASLEO coupling the properties will be in a next different study. But for this, we need statistics.
Did you do the reduction process automatically? No. Manually.
Yes. You mean not one by one, sorry, make like an iterative. So I have a code with an iterative process.
One star.
Yes, define background, define the mask, then adjust the mask, because some stars have a different threshold for the definition of the mask. Some are very close to other sources, and I need to constrain the mask with a. So I end the mask with respect to the percentage of the central flux. Most of these masks are limited to the point where the flux reaches 15% of the central flux, and then it stops. But some stars are close to bright objects, and I had to constrain this threshold in that sense. So each case was like an individual case, but the overall rule is that you have this criterion, the mask, then remove the principal component analysis, normalization, and pre-widening. So, just like in every study, I am very, very sure that this is a back-and-forth process. So I will return to this process again and again and again, like most of us. So it is.
A question about the yellow hypergiant. Is it a defining characteristic of yellow hypergiant to have underwent an outburst?
If there is no outburst, you can speak about the yellow hypergiant candidate, like in LBVs. So unless it was like a B star. So B stars do not show outbursts. They just...
not outburst, but they have underwent.
Yes, if they don't have
Yes, but this is more so. I would say that if you just look straightforward the spectrum, you can tell. While the other needs monitoring of the star to capture the eruption. So it's more tricky in that sense. Otherwise, it is a candidate.
Okay.